11.3 deals with geometric sequences and series. We had arithmetic, and the way we found that out was by minusing. In geometric, we're going to do the division of the ratio or the quotient, however you want to call it. We always divide left to right, like that. And so the first thing we're going to start to see is either one of these series are geometric. How do we know? We take left to right, and we divide, and we see what we get. If it's the same number, then it's geometric. If it's not, then we don't. 2 divided by 1 is 2. 6 divided by 2 is 3. I can even stop at this point, but I'm going to continue. This is 4, and this is 5. They're not the same. This is not a geometric function. Let's go this one. 27 divided by 81, if you put this in the calculator, becomes 1/3. 9 divided by 27, when you reduce this, is 1/3. 3 over 9 is 1/3. And 1 over 3 is 1/3. We have a geometric series because that ratio is equal. This is a geometric series. And we call 1/3 the ratio. That is called the geometric or common ratio. R is 1 over 3. Okay? This is how we work with it. Now, for a geometric sequence, we have the following formula. AN equals A1 times your ratio to the power n minus 1. A1 is your first term. N stands for how many terms you have, minus 1. Let's look at our examples and see how we play with this. On example 2, it says, write a rule for the sequence -8, -12, -18, -27. And then it says, then find A of 8. Well, first of all, we need to understand if this is a geometric sequence or not. With division, it's always going to be a positive number because negative divided by negative is a positive. 27 divided by 18 is 3 over 2. 3 over 2. 3 over 2. So I now know that my ratio is 3 over 2. So I can now write my rule. Why? All I had to find is this. I already know my A1. My AN equals -8 times 3 over 2 to the n minus 1. And that's where we stop. This is it. We put the first term, we put the ratio in. If you remember any of this, this is either decay or growth, right? This is what we worked with before. Now to find A of 8, that means my n becomes 8. This becomes A of 8 equals -8 times 3 over 2 to the 8 minus 1, or to the 7th. Really, you're going to put this in your calculator. This is not something you're going to do by hand, and it's going to come up to a very weird number. It is, the book says it's 2187 divided by 16, and this is with a minus. And I would say, I would do this the decimal way too. I would just say working in a calculator and give me the decimal. It's about -136.69. Okay, I'm good with that. I don't need the fraction here. But that's kind of how you find it. Geometric sequences and series are going to kind of give you decimals. It's not going to be perfectly worked out because of having to raise different fractions to powers. So it's not going to look beautiful. Let's look at example 3. I'm going to try hard not to erase my formula. I don't use this part at all. It says one term of geometric sequence is A3 equals 5. The common ratio is 2. R is 2. First of all, it says write the rule as A of n equals what? And then the second one, it says graph that sequence. And we'll look at that for a second for you to see what it means. Okay. I'm going to start with this, and I'm going to start A3 equals A1, I don't know what that is, times my ratio, which is 2, to the 3 minus 1, because this n is the same, right? And I know what A3 is, it's 5. 5 becomes A1 times 4. 3 minus 1 is 2. So my first term is 5 over 4. Now that I have my first term, I can go ahead and write it in here. This becomes 5 over 4 times 2 to the n minus 1. Okay, this is my rule. I'm good to go. Oh, they even use it. See, they're so inconsistent. 1 is a fraction. This they write as 125. I don't care. If I would have to graph it, the way they would want you to graph it is start with n being 0, well, n being 1. That would make this 1, and you get 5 over 4, which is a little bit more than 1 1/4, right, for 1. And then for 2, you get 2 times all that is a little bit higher. And it really, if you graph it, you're going to notice that it becomes a growth. I would say just go to y equals, put that in, that becomes an x, graph it. If you use your own calculator, please remember that needs to be in parentheses, otherwise you're going to graph it wrong, okay? And that's about it. I'm okay with you not doing the actual pattern of dots, but just give me the line. Example 3 plays the exact same way, but it's a little bit more crazy numbers, okay? Because now they don't give you either one of A1 or R. They just give you 2 random terms and you need to come up with a solution. They say this. A2 is 45 and A5 is negative 1, 2, 1, 5. And they want to find the rule for the nth term. What would that rule be? So here's what we know. We're going to follow this pattern over here. A2 equals A1 times R to the 2 minus 1. And let's go ahead and refill this and write this as 45 equals R times A1, correct? That's all we have. We don't have anything else. For my second one, A5 equals A1 times R to the 5 minus 1. Whatever number is here goes in there. Or negative 1, 2, 1, 5 equals A1 times R to the 4th. Let me write these in the right order. A1 times R. And R to the 4th. This is where we are, right? So, in order to solve the system, I would have to do the substitution. I'm going to say, okay, A1 equals 45 over R. I just divide by R. And I can take this one now and plug it in here. I end up with negative 1, 2, 1, 5 equals 45 over R times R to the 4th. So remember the rules of exponents. They get minus, this gets away, this becomes R to the 3rd. So I have 45 R to the 3rd equals negative 1, 2, 1, 5. I divide by that 45. R to the 3rd equals, I can't find my calculator. Never mind, I have the book. I keep forgetting I have the book. Negative 27, which means my R when you take the cube root is negative 3. Negative 3 to the 3rd power is that. So I found my ratio. Now that I have my ratio, I can go ahead and find my A1. A1 is 45 divided by negative 3 or negative 15. And now I can come back and actually write the rule. AN equals negative 15 times my ratio, negative 3 to the n minus 1. And we're going to leave it right there. So the way we did this, you're going to have 2 equations with 2 unknowns. We're going to substitute one of them, replace it in the second, solve for that R, and come up with the solution. Okay? Let's look at, now that we're done with sequences, and this is how sequences work, we're going to move on to geometric series. And as normal, they will have a formula for the sum of geometric sequences. This is what series are, right? A series is a sum of that particular sequence. So for the sequence, we had A of n equals A1 times R to the negative 1. For the sum, or for the series, this formula says it's, again, it's going to be A1, your first term, times 1 minus your ratios to the nth power over 1 minus your ratio. That is your formula. Okay, we have it in the book. We wrote it in the class. So let's go ahead and work on example 5. It says, consider this series 1 plus 5 plus 25 plus 125 plus 625 plus. The first thing they say is find the sum of the first 10 terms. Before we do anything, in order to find that, we know the first term. We don't know the ratio. So let's go ahead and find it. 5 divided by 1, 5, 5, 5. My ratio is 5. I can stop. Okay? So my sum of the 10th numbers, which is s of 10, it's going to become my first term, which is 1. You like that part? 1 minus my ratio. My ratio is 5, remember? To the 10th power over 1 minus 5. And I'm telling you, this is absolutely calculated or it works. I've done this math, and this math comes down to 2,441,406. Okay, I just plugged it in my calculator as it came because it's going to go bananas. Please remember, this is a parenthesis, this is a parenthesis in your calculator. This is a parenthesis. You're going to need a lot of parentheses to get this done correctly in a calculator. Also remember, you can use that calculator on the phone that I gave you and do it that way. It might actually help you with writing this correctly faster. But that's the number that we get in this case. It's a huge number because this is how it works. Okay. For the part B of example 5, it says find n, such as s of n will equal 3,906. And in order to work this, we will start with s of n equals a1, 1 minus r to the n over 1 minus r. This is our formula, right? This is our beautiful formula. The only thing that we know in this case is my a1 and my ratio. So this becomes 1 minus 5 to the n over 1 minus 5. That's all that I have in here, right? And I know that this whole sum should equal 3,906. I don't have a lot of room, so I'm going to go ahead and write this as a 4, because I need that as a 4. Negative 4, I'm sorry. 1 minus 5 is negative 4. I need to get rid of that negative 4, which means I'm going to times it over here and over here. This goes away, so I can get rid of it, right? And then at 1 times anything keeps the same thing, so this becomes 1 minus 5n equals, and that multiplication, believe it or not, I actually worked it out. It is negative 15,624. When I minus this 1 over there, because I really need to solve this problem, this becomes 25 because I minus that 1. And then I'm going to go ahead one more step and divide everything by negative 1 because I want this to be positive, right? So I'm going to divide by negative 1, which makes both of these positive. And now I go, okay, I need to find n. Do you remember when we did, I think it was chapter 7, exponents? How do we do this? If we don't know how to do anything else, we're going to take logs. We're going to take a log in this space and a log in this place. That's the only way to do it. Why? Because then that exponent comes in the front. And log 5 equals log 15625. To get rid of it, I'm going to have to divide by this log of 5, right? When you do that math, and I did it, all of it is calculator work, we end up with n equals 6. When you put those two numbers in your calculator, n equals 6. So it says for the 6th term of that, the sum would be 3,906. So a little bit more work, but not super hard. The last part of this chapter is example 6 and 7 that are word problems or real life problems that deal with the exact same thing. The first one, I believe, deals with your sequence. The second one deals with your sum. I'm going to let you take a second and read the problem, so please pause and then read your problem and come back. Okay, this problem deals with Taylor sums, and here's what we know. We know the average, or A1, is 80 points. Let me not make out stuff nice. In order to find my ratio, I know it decreases by 0.086. So this is going to become 1 minus 0.086. We're going to transform that percentage into a decimal, and I get that to be 0.914. This is my ratio. I can now go ahead and write that rule. That becomes AN equals A1, 80.9 times 0.914 to the n minus 4. That's the first part of your problem, right? Is write the rule for this sequence. The most important part of it is finding that ratio. If you know it's decreasing, Remember when we did decay, it's 1 minus R gives you that factor of decay or the ratio. You're going to have 1 minus whatever is decreasing, and that's going to give you the ratio that you need. For part B, it says what was the average monthly cellular phone bill in 1993. We started in 1990, 90, 91, 92, 93, which makes my N 4, which means A4 equals 80.9 times 0.914 to the 4 minus 1. Again, you're going to put this in your calculator, and you're going to come with about 61.77 roughly, okay? Then for part C, it says, when did the average monthly cellular bill fall under $50? So really what you need to know, when was this equal 50? So you're going to go 80.9 times 0.914 to the N minus 1 is to equal 50. We're going to divide that 80 out, right? This becomes 0.914 N minus 1 equals, and I use my calculator for this, 50 divided by 80.9. I'm just going to use the rule, guys. It's just so much easier for me to do it this way. 0.618. We divided that 80.9 out, right? And then from here on, we're going to take the log. Anytime you have a variable over there, you can't solve it. You need the log and the log. So this becomes N minus 1 times log of 0.914 equals log of 0.618. Then all I have to do is divide by log 0.914, get rid of this one, so that division becomes 5.35. I'm plussing my 1 to the other side, and equals 6.35. So in about 6 years later, from 1990, 90, 91, 92, 93, 94, 95, in 1995, about that time, your bill is 50 or below. That's how you found it out. Anytime you have to solve for n and n is the exponent, please remember chapter 7, I think it's 7, maybe 8, I don't remember, when we did the exponent, and that's how we solve it. Example 7 and the last one in this particular subchapter deals with your sum, and it's a word problem. It's the exact same model that we have up there, and it says, on average, what did the person pay for cellular phone during the 1990 to 1997? So here's why that is important. You have your model, you wrote that down. AN was 80.9 times 0.914 to the N minus 1. From 1990 to 1997, that gives you 8 years, right? We already know my A1 because it tells us my A1 was this one. I know my ratio. What I don't know to use this is all of the period of times that I need. So this becomes S of 8, because that's what we're looking for, is A1, which is 80.9, correct? Well, no, hold on. A1. Because that was just an average monthly bill, and I didn't read that problem correctly, your A1, instead of being just this, it's going to become 80.9 times 0.914 and times 12 months, because we needed per year. That bill was only for 1 month, and we needed for 1 year. So this becomes really, your A1 becomes 970.8, okay? So now let's rewrite this with the right first term. 970.8, 1 minus my ratio, 0.914, to the 8th, all over 1 minus 0.914. This is really heavily calculated work. We're going to plug in here, and we get about 5,790 would be the payment for cell phone bill in those years from 1990 to 1997. Again, the way we got to this, and I think we got this right in class, I just messed it up on the video, is this gave me, for my first year, for my first month, but I have 12 months in that first year, so I had to times that by 12 to get to this number. Okay? That's where we are. This is all for 11.3. I'm hand-picking your problems for homework, so I don't think you're going to have a hard time getting this done. And then I will see you back for 11.4. Happy homework.